Buenas tardes, estamos aquí en el Salón de Grados de la Escuela Técnica Superior de Ingeniería Industrial con el fin de asistir a la conferencia que va a impartir el profesor, doctor honoris causa por la Politécnica de Cartagena, Reiner Gadow. Professor Reiner Gadow is full professor and former director of the Institute of Manufacturing Technologies of Ceramic Components and Composites at the University of Stuttgart. Professor Gadow worked in different enterprises as head of research and development department and managing director, and visited Japan, the States, the USSR, France and China for research activities and invited lectures. The focus of the Institute of Manufacturing Technologies of Ceramic Components and Composites at the University of Stuttgart will be on modern production engineering for ceramic parts and components and the precision finishing thereof. And last but not the least, he's doctor honoris causa for our university, University of Cartagena. The title of the exposition is 3D Printing of the Bioceramics for Bone Regeneration Applications. When Dr. Gadow wants to stay with us, I think that is a good option.
But I think this works. Huh? So, welcome everybody. It's my great pleasure to be again here in Cartagena. It's a long period of cooperation. Today we met one of the directors of the Escuela and the vice president, and we could say that it is more than 25 years that I come to Cartagena. And in earlier years we had the focus on automotive, on big ship diesel engines, but for this afternoon I selected the subject of my focus of the last 10 years of my active research, and that was mostly dedicated to biomaterials. And the presentation which will follow now is the outcome of nearly 12 years of close cooperation between our colleagues from the medical factory in Freiburg. Freiburg is in the southwest of Germany, not so far from Alsace, from the French and from the Swiss border. And my colleague, Professor Anke Bernstein, she was the person who made all the tests, not only in vitro, but also, as I will show you, in vivo. And so at the very end, we were quite happy that this new generation of materials and this new type of processing was really valid for the benefit of the patients. So the subject is 3D printing, very popular in the last decade, and in this case for bioceramics, which are applied to improve, to enhance the bone regeneration, and I will talk about the materials, the printing process. I will introduce a special material that is called bioglass, and we summarize and conclude, and I will show you some further perspectives. Before we come in more detail, just a few informations about our motivation. Why are not only we, so many colleagues in Europe active in this field, and one of the main reasons is the demographic structure in nearly all European countries, and on the other side the extended expectation of lifetime of the people. So achieving 90, 95 years is nothing extraordinary today, and that is the reason why we need much more implants and other medical treatment for the elderly people. So if you look left-hand side, in the year 1910, so these are data from my country, from Germany, and you can see after 30 years of peaceful development and prosperity, there is a perfect pyramid, and also very interesting, there is a good symmetry between men and women. Yeah? If you go to 2005, where we had this data, you can see it is completely disturbed. We have a distinct asymmetry between men and women. That means there are more women, and the women get more and more elder. The reason is very simple. These are the losses, the human life losses in the 2 world wars. Yeah? But the more interesting fact is, if you go down to the younger part of the population, you see this is a very bad situation where less and less and less young people have to carry all the social cost and burden for the elderly population. Yeah? I will not give an argument against solidarity, not at all. But we have to face, we must not be very performing in the medical technologies. We must also focus on the cost, on the efficiency of these technologies, because otherwise the smaller the part of the population who is paying in the system, the less you can take out of the health insurance budgets. And if we look to the future, to the year 2050, you see it is even worse. It is even worse. The people get elder and elder, the asymmetry is more or less gone, but the burden for the active part of the population who is still active in work and contributing to the social systems is even more and more shrinking. And this is the background why in most developed countries, not only in Europe, the same is true for Japan and Korea, we have to increase our effort so that the market for medical products will have a successful development. So we have a broad variety of fields where we focus our activity. So this afternoon, my focus is on bone regeneration. That means the hard tissue structure in the human body. And there are various reasons that we need so-called bone grafts. One is fractures that can happen from children to elderly persons, to nearly everybody as a result of an accident, for example. Another field are diseases and degradation phenomena of the skeleton, which is much more often for elderly people. Osteoporosis is a typical large-scale disease for elderly women, and the worst field is bone cancer. And if the operation is successful and the cancerous tissue has been removed, there remains a weakened structure or a big hole or a deficit, and so we need the bone graft to replace it. And last not least, for the load-bearing parts of the skeleton, we need prosthetic devices for the hip, for the knee, for the fingers, and for vertebra and further important parts of our skeleton. And here we have to ensure that the hard tissue environment of the prosthetic device shows a good mechanical stability so that the prosthetic device can develop its beneficial functionality. A few statistical figures. So, for example, in the year 2012, more than 500,000 patients in the United States received bone grafts, and the cost for that was more than 2.5 billion, European billions, not US billions. So that means it is a very important cost factor, not only for the private insured wealthy patients, even more serious for the people who are a member of a public insurance, health insurance company. And this figure, this number is expected to double in the last 10 years ago. So it is a dynamically growing market just because of the same reasons as I mentioned before. So on right-hand top, you see a model of such an osteocarcinoma that is cancerous piece of the load-bearing bone in the leg. And so this is a typical example. If this weak zone is not removed or repaired, a catastrophic fracture will happen very soon. So where can we get the bone substance, the bone mass, the bone volume to allow all these successful surgical operations? So until now, if this is possible with respect to the individual situation of the patient, the so-called autograft is, some people say, the king's path to overcome the problem. So that means from the same individual, from the same human being, for example, from the Becken, from the hip, yeah, you make a little cut and you take out under 100% sterile conditions a small part, and you can use this in the maxillofacial region, for example. But the problem is that the volume you can take out is very limited. The advance is that you have an excellent compatibility. That means there is no, if the operation is correctly performed, there is no inflammation, there is no contraindication. But this is very stressful for the patient. And I know what I'm talking about. My younger daughter, she had 3 operations where they did remove the bone from herself and did implant it in the teeth area. So this is well established, but there are a lot of limitations. So the next field in green, the expert call it the allograft sourcing to get access to bone, to hard tissue material. And this is gained from other individuals of the same species. That means from other patients, for example. And again, we have a good compatibility, but the resources are also very limited, and the patient who receives the implant has the same stressful situation as in the case of the autograft solution. So for a couple of years, the graft from other species, for example, from a bone of animals, was very popular. So here we had nearly unlimited resources, but especially the bovine sources were used, but even if they did the very best to sterilize the bone, there was always a high risk of infection, and the compatibility was far from being perfect because the mechanical microstructure did not really fit to the bone of human being. And therefore, in the last 2 decades, the focus was on synthetic material, and that is exactly the subject of my talk this afternoon. So, if the technology is well elaborated, the resources are nearly unlimited. So, we can produce it in hundreds of kilograms, it's no problem. And if we select the right material in the right microstructure, the compatibility is also very good. And this is called the alloplastic. The alloplastic. Yeah? And I will show you the further important field. If we look to the mechanical structure of bone, this is not a homogeneous material. In the outer sphere, for example, of a bone from the human leg, we have a very dense structure because here we have the load bearing. In the core we have a structure like a sponge. Yeah? And last but not least, in the center we have the bone marrow, a lot of blood vessels and nerves. That means all these structural properties are of highest importance before we can develop the concept for the final operation. Yeah? So if we look to the chemical or to the mineral composition, the typical human bone consists of about 1/4 from water, a further quarter from organic substances, mainly collagen, and 50% are inorganic materials. And here the calcium phosphates and the calcium carbonates play the predominant role. That means at the first look we have to analyze in detail the chemical composition and to analyze the microstructure by computer tomography, for example, and then we create the substitute from these two or further components. Which are the requirements for bone replacement in general? First is the biocompatibility, because the bone that we want to replace is not extracted and just working in laboratory. It should work in the physiological environment of the human being, of the human individual. But we want more. So this implant or this component for replacement should be osteoconductive. That means it should stimulate the hard and soft tissue surrounding so that there is a good ingrowth behavior, but not only a good ingrowth behavior, a very good compatibility, so that the load bearing can only work and the stress transfer can only be performed if there is a very good cross-linking between the implanted material and the surrounding material. So in many cases we have implants, for example from superalloys or from titanium, that remain for a long period in the human body. But this is not my subject for this afternoon. In many cases, we want to implant a material which will keep its structure and original chemical composition only for a period between 4 weeks and 4 months. After 4 months, for example, it should be completely converted in our natural bone, so that we can hardly separate it, which was the implant and which is the original bone, the surrounding. That is the standard, that is the state of the art in science and technology in recent years. Nevertheless, we should not forget that the hard tissue, like bones, have to perform mechanical properties. If you are walking down the stairs and so on, so it is a cyclic loading, that if it is a metal structure, you have to think about Wöhler's number for fatigue. The same is true for ceramics and bone materials. And that means we have to look for implant materials that are compatible from the physical point of view. So elastic modulus, strength, hardness should fit very well. I remember when I was a young researcher, one of my first theses were on the field of carbon fiber, carbon composites for prosthetic devices. So we had excellent partners on the medical side. Operations at the beginning were very successful, but the problem was this material had 10 times the strength of natural bone and also much higher elastic modulus. That means the load bearing did happen only for the implanted synthetic device, and the surrounding was not well connected, it was degraded. Because the bone has only a small or a minimum of genetic information, it grows or it shrinks if it gets a mechanical signal that there is a load. Yeah? And, opla, yes, I have it. Here, my screen. Yes. So, what does this mean? Don't know. This is self-acting. The density we are talking about, because of the high porosity, about a lightweight material. The density is between 1.7 and 2 grams per cubic centimeter. And this is the natural bone. So the hydroxyapatite, which is the synthetic bone material in pure phase, has a higher density, 3 to 3.1. The bioglass comes closer to the natural bone. But you see, if we look to the compressive stress, and here we compare the best compatible materials that are available, we always have a much higher mechanical strength for the hydroxyapatite, HA hydroxyapatite, and for the bioglass compared to the natural bone. In the case of the bioglasses, the Young's modulus, the elastic modulus, comes very close to the natural bone. And that is the reason why this relatively young class of material has become so popular in medical science and technology. Should not forget, it was an Englishman, Professor Larry Hench, who is called the inventor of the bioglasses. And I remember also as a young researcher, if you think in such a sensitive mechanical structure, why should I integrate glass? So we know glass has a sensitivity to fracture, so we don't like to work with this material, no? The reason is, this is not a silicate glass as we know it from packaging and so on. This is a glass that has a chemical composition which does perfectly stimulate the metabolism to have natural bone cells growing on its surface. That is the main background. So, Pepe, you know that the people in geosciences and in chemistry, they always want to see a phase diagram. And here we have this ternary phase diagram, right-hand upside, where we have silicate, we have calcium oxide and potassium oxide, and in this triangle you see the fields with the field A is the materials combination that can perform a good bond, bone bonding. The field B is the bioinert material. The field C is the resorbable material. That was one of our focuses in recent years. And that is the beginning that we don't know what use is here. That we need all the relevant data about the phase composition, the chemical composition, and last not least, we need the mechanical properties of these materials. And the first tests are done in vitro. There are some standard solutions. There are some standard solutions where the ionic species interact with the synthetic device, and then we look what are the species that are formed as a result. So here we have such a simple plate, a flat geometry, and there is the hydroxyapatite material selected, and that is the surface of hydroxyapatite after the implantation. And now we look what happens at the surface. These are the typical ionic species which in the aqueous system exist and occur, but we also have a certain dissolution of the calcium cations, of the phosphate anions, and in the solution they form the bone cells. The bone cells. And the bone cells, they start to sit on the component surface. If you do it in the most appropriate way, it can be a perfect cover of the synthetic structure. And that is essential, and that is what we want to achieve. So a good equilibrium between the physiological solutions and our artificially modified surfaces of the implant. So I will come back to that later, but in this early phase I want to give you one information. This model is working very well and is correct for solid bulk material. But in the human body and in the typical geometric structures we are dealing with, we have to deal with porous materials. That means the interaction does not only take place at the outer surface, but we have access to the inner surface, so that the pore design, engineered porosity, is crucial to have the best fit. And that is what I want to show you in a minute. So, bioceramics and the requirements for bone grafts. That was my talk until now. And we can say that the porosity we have learned, we have analyzed from extracted pieces of human bone shows that always under the condition that we can avoid any inflammation and infection. That means that we have perfect sterile conditions during the operation. And so we have a distinctly enlarged specific surface as not only the outer surface, that the total accessible surface is involved, and we have a very good ingrowth of the bone cells. And in a second step, and on a longer time range, not only the bone cells, even the blood vessels. That means the complete metabolism of a human being is used and applied to restore the original defect in the skeleton structure. And therefore we have to select materials that have a relatively fast degradation and a low density, and at the very beginning the mechanical strength must not be so high, because the patient in the early phase after the operation is stabilized by other means. The important thing is what happens with the implant after a few weeks. And fortunately, our colleagues in the medical faculty in Freiburg, they are very experienced to get the allowance for animal tests. And what you can see down left-hand side, that is the typical standard cylinder. We produce a few hundred pieces per day or per week. And this cylinder is implanted in the femur of a rabbit. That is shown right hand down. In this case, the material was not hydroxyapatite and not bioglass, it was tricalcium phosphate. That is the number 3 in the field, TCP, tricalcium phosphate. It's also very close to the natural bone. The advantage of tricalcium phosphate, it has half an order of magnitude faster resorption rate compared with hydroxyapatite. That means it is an optimum material. And now look, the image left hand, you can clearly see the cylinder. There is a perfectly fit of the bore, yeah? And we can see the cylinder in a good contrast by X-ray analysis. And after 6 weeks, it has not changed so much, but we can see there is no infection. There's no problem. After 12 weeks, you can see that the contrast is weaker and weaker, and the material is resorbed and rearranged. And after 26 weeks, you can hardly separate with this femur. Right hand side is the natural material, left hand is the resorbed implanted cylinder. We must really look in detail to see, okay, that was the implant. And this resorption concept, and under the load stresses that in this case the animal has to take, because the animal is not killed, the animal survives. Yeah? We have this excellent incorporation of the originally porous ceramic structure, which is more than 90% converted to the chemical and microstructural composition and structure of the original bone. That is the concept behind it. Okay, that was in a few minutes shown what was the work for more than 4 or 5 years. And then the next phase of this joint project came, where we did apply our experience and abilities in the 3D printing technology. And here we have some schematic draws. What is the beginning? The beginning is the selection of the appropriate chemical composition and phase composition and crystalline composition of the powders. Then we need special additives to improve the 3D printing process, and a dispersion medium, which cannot always be simple distilled water, but in some cases is a combination of solvents that show the best results. So then we create, by the application of well-established ceramic technologies, a suspension with a very high solid content. And with this material, we go in an apparatus shown right-hand side, that is a so-called spray dryer, a big apparatus, in this case working under the conditions of the pharmaceutical industries, that means with high cleanliness and so on. And we take the suspension and we use a special type of nozzle, and we build a spray. And there is a counterflow of hot air, so that the little droplets form more or less perfect little balls, and the balls will dry, and following the gravity we have on Earth, the product is collected at the bottom. That means the intermediate product, which is used for all the printing processes, is a special blend of bioceramic powder. Okay, so there is an option that the powder is coated with special additives. I will come back to this in a minute. And then we have to work with the typical engineering disciplines. The first is the CAD model. Yeah? And because of many reasons, we start with such cylinders, and we select a relatively coarse porosity, and this porosity is selected because of various reasons. And so typically, we know this since more than a decade, typically a medium pore size between 100 and 150 micrometers is perfect for the cell growth over a larger diameter or wall thickness. Therefore, it looks a little bit crazy. It is the macro porosity that is engineered. And the component is made by the 3D printing. 3D printing is the forming process, but for a ceramic material, the forming is not enough. After the forming, we have to select the appropriate heat treating. That means the material must be sintered. And sintering for such a porous structure also means a shrinkage. And this must be overcompensated by the calculation in the CAD model. So the typical linear shrinking rate is 15 to 20%. Yeah? That means the sintered part is distinctly smaller than what we call the green part that is coming out from the machine. So today we have a broad variety of 3D printing machines, 3D printing processes. The most established one is shown in this slide, where we are working with a powder layer, an individual powder layer that is spread for each individual step. And in the middle of this image, you can see there is a hydraulic cylinder, a high precision mechanic arrangement, and this is removed step by step, 10, 20 micron, and then we are scanning the surface with a laser or with another typical radiation for the hardening operation. And after this layer is finished, the machine moves downwards, and from the feeding chamber with a coater roller system, we fill it up with the raw material. Again, we have the projection, and so step by step we form the 3D geometry. The excess material is wiped out to the right-hand side, and normally these materials are recycled, so there is not much material loss. What we need in our case is a best fit of powder so that the powder flow behavior is appropriate to this type of processing. And in the second step, how do we glue the particles? So in powder metallurgy, the people use a relatively powerful laser beam so that the material in the outer surface is molten, and after the melting is consolidation, so the material is sintered. This is not appropriate for the bioceramics, because if we had a high pulse laser on it, the material will show decomposition and degradation. So it was a certain breakthrough that a very thin layer of a polymer material was the solution, and then we need a printer, which is also much cheaper than a laser scanning device, and the printer gives a little droplet, and like a printing operation of a sheet of paper on each individual layer is gluing together the individual particles. Yeah? That means step by step, layer by layer, by a printing operation, we form the green part. Yeah? So this, the central part of the apparatus is called the build chamber, and as I mentioned before, layer by layer, we introduce a perfect even powder layer, and then the process starts again. If the geometry of the component is completed, it is carefully taken out, the excess powder is separated, and then the part goes, in analogy what I have said before, to thermal treatment, careful at the beginning, and then to the sintering operation, so that we have finally the component that is ready for surgery, for medical application. The advantages of this printing process: it is very fast, relatively fast. The cost of investment is limited. It is not a machine where you have to invest €1 million. No, such machines depends on the size for sure, but in a range between 150 and 250, 300,000 euros, you can have a perfect computer control device. There are several printing heads available with different resolutions. The construction is relatively simple, and very important for the component, we do not need microscopic supports, because the powder bed has enough stability to keep the component in the correct position. Yeah? And last not least, we have unlimited ability to recycle the excess powder material. That makes it very cost effective. The drawbacks is that the green density, the original density after the forming process, is relatively low. And the same is true for the mechanical strength in this state. And the geometric resolution is also limited. Yeah? There are alternatives, but that means longer process times and a factor of natural numbers higher the budget for an investment. So, to go in a little bit more detail, we start with our CAD file. Then is the next step, which is quite well known and established in computer-assisted engineering disciplines, that is the tessellation, where we obtain the so-called STL file. The STL file also for each step in the layer structure. And STL means Standard Triangulation Language. And I hope the contrast is good enough so that you can see these blue lines and crossings. That is just a geometrical assisting structure to describe such a geometry. And as we are using this for each slice in the structure, the operation is called slicing, and we end so that there is a transformation of the STL file in the SLI file, and that means sliced layer interface. And in such a simple, the first look, simple cylinder, we can have a distinct variation in microstructure from the bottom, from the first layer to the intermediate layer and the top layers. We have a high degree of freedom, but at the very end, that is the programming of our machine, where step by step the material is connected, the powder bed material is connected by our printing device. To be successful with this concept, it is essential that you have the know-how in ceramic technologies how to produce perfect spray-dried granulates. Because until now, you can hardly get these materials available on the market. And fortunately, we had two of these machines, a smaller one, which corresponds to pharmaceutical standards, so that we produce in lot sizes between 1 and 50 kilograms these powders ourselves. And there were some research, including thesis in process engineering, to develop two fluid nozzles, because the spray-dry operation is not only depending on the heat and mass transfer in such a counterflow apparatus, it is strongly depending on the type of the sprayed particle in liquid state, yes, in liquid state. So that in the center we have the ceramic slurry, the ceramic suspension, and in the outer shell of the nozzle we have compressed air, in some cases also compressed nitrogen, and then the dimension of the nozzle is selected and optimized step by step, so that the particle morphology is obtained as desired. Further important properties is the viscosity of the suspension. All the suspension properties are essential. Solid content, viscosity, the volume flow, the pressure, the opening size of the nozzle, and the spray drying parameters in such a device. So that was really more than a year work to obtain the appropriate set of reproducible sets of parameters to obtain the appropriate powder material. That is like it looks. So the aim and scope for spray-dry granulation in general, but especially for the bioceramic suspensions, is that we obtain spherical particles with good flowability, and these particles consists of a few thousand primary powder grains. So we are at least 2 orders of magnitude difference between the raw powder and the intermediate product. As you can see here, these typical ball-like structures, they have a size, these ones here, between 30 and 70, 80 micrometers. The original powder is a submicron fine type. So that means in the suspension we have this fine powder, and after the spray dry operation we have these little balls. And the reason is that if we would use the fine powder, this material cannot be processed. Not at all. It will stick. Yeah? So this is essential, and so for example the beta calcium phosphate, beta TCP suspension was used, and there is a very high solid content, up to 70%. The difference in this case was water. There are some special polymer surfactant additives and a small amount of binder like polyvinyl alcohol, for example. And as I mentioned before, the original powder is passed through a fine milling in an attrition mill, and in any case the primary grain size is smaller than 1 micron. Smaller than 1 micron. That means out of the box of the supplier, this is a very fine material. Then we have the milling operation and the high value adding by the spray drying granulation. So there are sometimes agglomerates. I will not go in so much detail with the ceramic technologies, but just to show you on the right hand side, if we have the spherical granulates, the green material has a very limited flexural strength in a reference sample. So these tricalcium phosphates typically are sintered at a maximum temperature of 1300 degrees C, depending on the grain size, in the range between 1 hour and 5 hours, for example. There is a maximum, this case for the 1 hour thermal treatment time, and we see a flexural strength of 6 megapascal is not so bad for for a printed material. But if we use this additional attrition milling operation, that means we have a much better homogeneity in the suspension. We can nearly double the strength. And here also the longer sintering time is beneficial, so that we obtain a material with a flexural strength up to 12 megapascal. And so typically the desired value is around 10 megapascals, so that this goal could mostly be achieved. Yes, now a microscopic or mesoscale look what happens during the 3D printing operation where we use a binder. You see in this slide the spherical powder particles. The powder is coated, and what we introduce by the printing head is just a very, very small droplet of hydraulic fluid. Mostly water with alcohol, some additives, or acetone and some additives. And thereby, the original coating at the contact point there is some dissolution by the solvent, but the amount and the evaporation temperature is relatively low, so that the drying process is exactly similar to what you know from printing on a sheet of paper. That means after 10 seconds, 20 seconds, it is dry. Yeah? And it keeps the structure, it remains stable. Yeah? So the binder is brought into the powder by blending, that is one solution, and the second one is by coating of the operation. And that was another research field in our institute, the coating of ceramic powders, for example, to create very complex zirconia materials. And if one has this know-how, it is easy to adapt it for such other purposes. So here you can see the green parts on the fracture surface, and you see in the middle there is a bioglass material after sintering at 950, and the beta TCP sintered at higher temperature, 1250. It is a relatively porous, weak structure. So at the very beginning we thought, oh my God, with such a weak structure we shall never fulfill the requirement, but fortunately that was not true. Step by step we could increase the green density, and for sure step by step we could optimize the sintering and for sure also the printing conditions, so that the appropriate desired geometry was obtained. So here you have a selection. So for easy understanding and comparison, you see a match light. Yeah? Match light which has typically dimension 2 by 2 millimeters. Yeah? And in the case of these implants for rabbits, we remained in a sample size in the diameter less than half a centimeter, and the maximum length can be varied according to what is desired. So there is a variation of the geometry and the porosity depending on the material properties, the printability, and this stratospheric complex structure was achieved by the same principal processing, and the design is coming from colleagues from the Vienna Technical University and the Faculty of Medicine. They want to have these structures because they have a much higher compressive strength. That means the learning by doing is also to learn from the colleagues in the neighbor disciplines, which is the most appropriate structure. In one case, the focus is on the dissolution reprecipitation behavior, that means the ingrowth behavior. On the other side, the people in the maxillofascicular application, they want to have a relatively high mechanical strength since the early beginning. Yeah? So I showed you this femur bone of the rabbit, and let me show you here another response in the so-called reference fluid, where you have stem cell solutions, stem cells of a special type that are used and can be made visible by a contrast additive. So that the question was, you see, some of these materials, you know from the mineral composition, they have a certain basicität. They have a pH more than 10. Yeah? And this is not beneficial for a sensitive cell culture. Or on the other side, it can be on the acidic side. It's also crucial. Yeah? So the standard process in modern medicine is to use these stem cells and then study over a certain period of time, and you can see if the cells are dying, it gives a result, it is orange-brown. If it is such a green and such if you look here, 7 days, 10 days, a more or less dense layer, that is the indication that you have a perfect cell growth with no undesired chemical interaction with the substrate. Yeah? And that was not clear at the very beginning, because many of these synthetic materials can show a sensitive reaction against these stem cells. Yeah? And that was a unique work of Professor Bernstein. Unfortunately, she died when she was just 54 years old as a result of an accident when she was mountain hiking. Yeah? So it was really a catastrophe. Okay, now I will refer to the research work of Dr. Esslinger. He was one of the latest PhD students, and he had a completely different concept, because our faculty spent a lot of money so that we had all the technologies available for 3D printing, everything, laser, melting, and so on, and so on. And here we have the filament deposition modeling or molding. What does it mean, a filament? So we take an appropriate plastic material, we fill it with these ceramic species, and then by an extrusion machine, it is like a very, very fine cylinder, a few kilometers in length on a big wheel, and by a high precision drive, this material is extruded, and the thermoplastic material is heated in the head. So it is the printer is a micro extruder, so that the structure is built strip by strip. It was at the very beginning, it was a training option for our students, and then we learned, okay, there are some limitations with the graphical resolution. You can make the strip not finer than the finest nozzle of the micro extrusion machine. But if you, and again, therefore, the reference to the matchlights, yeah? Some people make little ships and models from matchlights, yeah? By a clever arrangement. Here we have just the rectangular arrangement, yeah? So 90 degrees offset, yeah? And then layer by layer, we can produce a structure. And Esslinger's concept was unique. He said, oh, I will not make directly the structure of bioceramics with that technology. I use it for the mold. And then the mold is my negative. And in this porous open structure, we fill the ceramic suspension, the so-called slurry, let it coagulate and dry, and then we remove the dye. The dye is a lost dye, yeah, for each component. And by the way, he did achieve such a perfect rectangular structure. You see the intermediate product, the yellow-brownish is the polymer, the form, and right hand down, that is the final sintered product. Yeah? It is not so different from the printed materials I showed you before, but the nice by effect was, it's more a secret that this machine system did just cost 12,000 euros. That was a tenth of the original printing machine. So even with very economic means, you have access to such interesting material. Okay, so again, there is the process chain. You begin with the CAD modeling. Then you have to establish your printing techniques, the additive materials, and also the software for all the slicing. operations. But what was interesting here is what is the behavior of the ceramic material when we fill up this polymer form. Yeah? And here we have a plot to show the viscosity depending on the shear rate. And you see, for example, the bioglass has a very high viscosity. If you steer it, or you use another magnetic device, for example, to reduce the viscosity, it works well. The beta TCP had a low viscosity, more or less independent from the shear rate. That means the material was very easy to handle and to manage. And that was the reason why his focus was so strong on the tricalcium phosphate materials. At the very beginning, so Stefan Esslinger is a guy of my size. I saw him with tears in the eyes. He was completely disappointed when he sintered the first sample of his bioglass bodies, because he was a classic mechanical engineer. He was not a chemist. And the surprise was that the bioglass did not keep its original form and shape. It, following the gravity we have also in our laboratories, the powder compact body did collapse. Yeah? So we had to restart the program again, and then step by step, by the change of additives, by the modification of parameters, at the very end, okay, it did work, that also with the bioglass as raw material, we could achieve such samples. So, as I mentioned before, the dye is a lost material, and it is separated from the ceramic body. You cannot separate it mechanically because they are interpenetrating each other, the phase. So it must be under oxidizing conditions, it must be burned off in a controlled manner, controlled combustion. And it is not so easy, because what happens is that the material, as a result of the heat treatment, shows early shrinking behavior, and so we get shrinking cracks. Yeah? That is what we can see left hand below. But with learning by doing, step by step, and that is what you can see right hand side, the radius at this bore, the radius was one layer of extruded dye material. And so it is not so perfectly smart, the geometry, but for the ingrowth behavior in bone replacement doesn't matter, it's perfect. We can work with such a surface. And here we have different views on top of the sample, front, side view with variation of the contrast. And you see the most important thing is this open porosity for the large scale pores, 100, 150 micron diameter or height. The other thing is the micropores, and here we need an electron microscope to see in the middle down, you see with a high resolution, there is a second type of porosity which is in the far submicron range. So we have two porosities. Yeah? It is a bimodal porosity, and the macroporosity is essential for the ingrowth and the formation of blood vessels, and the microporosity, in combination with the chemical nature of the material, gives us the instrument to modify the resorption speed, the resorbability. Yeah? Okay, so it started very easy, but then we learned it is more complicated, but that is exactly what science is asking from us. So in the first step, let me summarize and conclude. Bioceramics like bioglass, calcium phosphates, and composite materials made from these species, they could be processed to suitable powders for 3D printing by ceramic technologies and this spray dry granulation. The 3D printing was successfully used to manufacture such scaffold structures with high porosity, but also, that is the payoff, low compressive strength. The interesting fact is that the in vitro test showed a good biocompatibility of the printed structures, and in further experiments and further development, the focus was on the improvement of the mechanical strengths with much more sophisticated structures, because a part of the bone is called spongiosa. It is exactly the same if you look to the teeth. We have the dense outer shell, and the core of the teeth is also spongiosa. So that is now the state of the art in the current work. So for those who have not yet seen Stuttgart, you see, even in Stuttgart we can have such nice weather as we had in Cartagena today. Okay, so just to give some additional comments, today's implants, there is distinct growth in the market for hip joint prosthesis and for knee prosthesis. And you see that the knee prosthesis market is growing a little bit faster, and I'm always a little bit nervous because in a not so long period I have to face such operation myself. And here again we can support the success of the operation by introducing such synthetic bone materials. So some further statistical data, here we can see that in the United States the knee replacement is by far faster growing than the hip replacement. And that is also an outcome, because that the people today, they don't want just to keep their standard life. No, they are demanding the same mobility as a young person in advanced age. And that is the reason why this market is going forward so strongly. The hip is not only the prosthetic device of the femur. So if I remember the last summer weekend, the first summer weekend in Germany with the motorbike drivers, 150 horsepower, the gas hand, and going around with a speed of 200 kilometers, and one crash after the other. So there are many young persons who suffer extreme fractures in the hip area. And you see here an example where we have titanium structures integrated. So it is also hybrid solutions where we are working on. Yeah? Metal structures for implant device that remains for a lifetime, or at least for 10 years. And on top, the bioresorbable material. Left hand below, you see the situation where there was a severe damage of the front shell of the skull. Yeah? And in former times, they were using a silver coin. A goldsmith did prepare it. Yeah? That is, if you look to the famous movie of Moby Dick, that was used 200 years ago on the sailing ships if there was an accident. Today, you make the scan, you have the 3D data, and we produce exactly this shell so that the element fits in the deficit structure of the patient. And not enough, right-hand side, you see that this is not a prosthetic device that is integrated in the human body. If you think about all the poor guys that are suffering now in Ukraine and other war theaters, these are modern, ultra-lightweight prosthetic devices for external applications. So here we use the knowledge in biomechanics, so that this, you see, this structure consists of very thin filaments, but it follows directly the main stress axis of the structure, and it has a lightweight character, not even 10% compared to a classic prosthetic device. So that is also a field for 3D printing, not only what I showed in the first part of my presentation, so it is a more broader application field. And last but not least, we see here that the 3D printing is really a promising technology in the field. So we have here the case of a vertebra, or in the case where we have polymers, the trachea. So if the people suffer from cancer or another accident, until the complete replacement of a jaw, also a typical result of a biker's accident. Yeah? And therefore the medical partners were essential for us and will be essential for the future, because we are the partner who helps with the material and process technology. The decision-making people are the medical doctors. So thank you for your attention, and I hope that this unusual field did meet your interest. Thank you. Questions? Comments?
How is the cost of, for instance, lift? So, the cost of the expensive.
So the raw materials.
Es que se está grabando. Online.
Okay. So the raw materials like hydroxyapatite or the tricalcium phosphate, we are working in laboratory size, not in a real industry capacity. So it is between 15 and 25 euros per kilogram. Yeah, that I think is quite reasonable. If you see the final cost for such a medical application, that is not a limiting factor. Yeah? And for the bioglass, it's even much cheaper. It's less than 10 euros. Yeah?
No more question?